Alright, so today's topic is the Diels Alder reaction, which is a pretty well studied reaction, and it goes a little bit like this. So say you have two molecules that look something like this. The one on the left is what we are going to call a diene, and the one on the right is what we're going to call a dienophile. So diene should at least make sense to you. The di just means you have two, and ene is typically the suffix you use for a double bond. So there's two double bonds, and what's special about them are they're in conjugation, which means they're in this sort of one space away configuration where their electrons are allowed to, I guess, overlap. So you have a bunch of p orbitals lined up like that. That's called conjugation. Dienophile, we'll worry about why it's called a dienophile in a little bit, but for now, just say that, okay, it's got a double bond, and it's got some groups off of it that we'll talk about in a little bit. So the way that the Diels Alder reaction works is that it's called a cycloaddition reaction. So here, this dotted line here just represents, I guess, it's not really a bond, it's more like where this bond is moving to. So in the Diels Alder reaction, everything is either going to move clockwise or counterclockwise. It doesn't really matter as long as you have a cyclic movement of these pi electrons. And if you follow the arrow pushing that I've drawn here, what you get in your final product is a new six-membered ring with a double bond on the backbone of where the diene used to be. Okay, so you probably have a lot of questions when it comes to what exactly is going on here, and that's what I hope to clarify. So this is a very intricate reaction. It has a lot of pretty cool, well-studied reactivity, so let's dive in. Okay, so what's the first question? So the first question is, one, why do we need a diene, and why do we need a dienophile? So why are these two functional groups what we need here for the reaction? Let's review a little bit of what you should know from taking a first semester organic chemistry. One rule is that whenever you have a bond formation event, that occurs when you have a filled orbital and an unfilled orbital. And the filled orbital is going to donate electron density into the unfilled orbital, and that's how you're going to get the formation of a bond. Remember, a bond is simply the combination of two orbitals. The second characteristic of a chemical bond is that it requires good spatial overlap of the orbitals that are involved. Say you have two p orbitals, they combine on axis, that makes a bond. And the reason that works is because they combine with the correct symmetry. We'll talk a little bit more about that as well in a little bit. The third requirement is that the orbitals need to be similar in energy. If they're too different in energy, they're not going to mix that well, and you're not going to get a stable bond. Okay, so what do we mean about that in the context of a diene and a dienophile? Okay, so say we have our diene. The molecular orbitals that are associated with the diene are going to look like this. And you're like, okay, what exactly is going on here? Well, remember, we have a conjugated pi system. So we have two pi bonds that are conjugated. So we look at all of the p orbitals that are involved there. And the lowest lying orbital is going to be when you have all the p orbitals lined up perfectly. There are no what we call nodes here. Over here, you'll see in this bonding configuration here, we have these guys combining in phase, and you'll see a node here where you go from shaded to unshaded, or black to white. This is a change in the phase of the orbitals, and this region here is called a node, where no electron density can exist. As you go along, the third bonding configuration, what we're going to call the anti-bonding orbital, the first anti-bonding orbital, you have one node, two nodes over here, and in the third one you have 1, 2, 3 nodes. Because you have so many nodes up here, this is going to be extremely high in energy. This is the second anti-bonding orbital. The bonding orbitals typically are going to be filled with electrons. As you see over here, both of these are bonding orbitals. They're filled with electrons, and over here these are the anti-bonding orbitals. What we're going to call the HOMO stands for highest occupied. If you haven't heard these terms before, HOMO is highest occupied molecular orbital, and the LUMO is the lowest unoccupied MO. See if I could fit that all on here. Okay, so the lowest unoccupied, so the first anti-bonding orbital. So again, This is a bonding MO, this is an anti-bonding MO, this is a bonding MO, this is an anti-bonding MO, and this is all for the diene. Okay, well, let's also look at the dienophile. The dienophile just has one pi bond that we care about, and has these R groups, these substituents that branch out. So since it's only got one pi bond, you only have a bonding orbital and an anti-bonding orbital. This is what you should be familiar with from Organic Chemistry 1. Okay, so let's see how these make sense in the context of the rules that we're given. We want to form a bond or bonds between the diene and the dienophile. We have a few requirements, and those are going to be these requirements. So in the context of our system, if we say we're looking at Rule 1, again, Rule 1 says if you want to make a bond, you need bond formation between a filled orbital and an unfilled orbital. Well, when we're looking at our diene and our dienophile, the filled orbitals are over here and the unfilled orbitals over here, and we want a bond between the diene and dienophile. So our two options are take the filled orbital of the dienophile and react it with the unfilled orbital of the diene. So we have two options here. This orbital can interact with this one, or we take the filled orbital of the diene and react it with the unfilled orbital of the dienophile. So then again, you have two choices. You have the interaction between this orbital with this orbital, or this filled orbital with this empty orbital. So there's four possible combinations we have here for the bonding that could work out. Okay, but we still have two more rules, so let's look at those. The second rule is that for the formation of a good chemical bond, you require good spatial overlap. What that means in the context of most bonding is that you need good symmetry. Okay, so the only times that the symmetry works out for this bonding arrangement is going to be in these two configurations I have here. You'll find out later when we look at the mechanism, when you have the overlap, it's going to be between this area here and this area here. So white-black needs to match up with white-black if these are going to bond. Similarly over here, white-white matches up with white-white, so these could bond. The reason that this can't bond with this is because you have white-black, and this you have white-white. So this bonding configuration doesn't have the right symmetry. The only two configurations that have the right symmetry are the ones that are indicated here. So the green pairing and the red pairing. So to restate, Rule 2 lowers down the four possibilities that we had previously that a filled orbital had to interact with an unfilled orbital. It says we also have a symmetry requirement that only orbitals that have the right symmetry or spatial alignment can participate in bonding. Alright, and then we have this last rule here that says bond formation requires similar energy orbitals. So if we look at an energy diagram for the remaining orbitals, previously it was unscaled, now it's going to be scaled. We see that one of these has a larger energy difference than the other. So the homo-lumo pair from the dienophile to the diene has a larger energy difference than the homo-lumo pair from the diene to the dienophile. So this actually comes from calculations, but what it shows is that the green combination, the homo of the diene with the lumo of the dienophile, is lower in energy. What that means is that they're more similar in energy as far as the orbitals goes, which allows us to make the final conclusion that for the Diels Alder reaction, you are going to need to look at the diene homo and the dienophile lumo. Okay, so that takes a little bit to take in. If you didn't understand the previous arguments, go read your lecture notes, then come back, watch the video again, and then maybe it'll make a bit more sense. Let's try to consider the situation where we don't have a diene and a dienophile. So say we're just like, okay, how about we do a cycloaddition reaction between two alkenes? Well, the problem there is that if we just have an alkene and an alkene, we try to do a cycloaddition, the problem is, again, they don't meet up with the three rules that we had, right? So rule number 1 is that we need to mix the filled orbital with an unfilled orbital, or a filled orbital with an unfilled orbital. But rule 2 states that you need the right symmetry. So here is our filled orbital, here's our unfilled orbital. The problem is this is black-white and this is white-white. So no matter how you rearrange these two bonding arrangements and try to get them to meet up, they're not going to work out as far as symmetry goes, and they're not going to have a favorable bonding arrangement. What that tells us is that we require that conjugated to alkene, that diene, because it has an MO that matches the bonding scheme of the dienophile. Okay. So, what's our second question as far as the Diels Alder reaction? Why do we require EWGs and EDGs? Well, you're probably like, what does that mean? So an EWG, I don't know why this is orange. An EWG is what we call an electron withdrawing group. An EDG is something we call an electron donating group. Okay, so a donating group is anything that can contribute electrons, such as a lone pair, into the pi system that we're looking at, and an electron withdrawing group is anything that takes it away. In other words, the real question is, if we have a diene and a dienophile, and we propose this sort of cycloaddition reaction, why then do we not actually observe this event occurring in nature? So this reaction does not occur. Doesn't work. And the question is, why doesn't it work? Why did the first reaction work that we talked about and not the second reaction? Okay, so in addition to the rules we had before, we have two more. Electron donation into an orbital generally increases the energy of that orbital, and electron withdrawal from an orbital generally decreases the energy of that orbital. So let's look again at our bonding scheme that we had before. I'm going to try to simplify this. So we had at first the diene, and it looked like this. These are the energy levels of its orbitals, and we also had the dienophile. Ignore this for now, and ignore this for now. So, in the reaction that we're considering right now, the reaction doesn't happen between diene and dienophile. But if we have an electron donating group on the diene, what that means is that you have electron density being donated into this HOMO. So you have some sort of group on this molecule. It's a substituent, say an oxygen over here, that is donating into this system. With the increased electron density, the energy of this orbital will increase. On the dienophile, say you have the opposite. You have an electron withdrawing group, an EWG. So that's like in the first reaction we looked at over here, if you have this carbonyl compound over here, that can, since the oxygen is electronegative, that's going to be taking electron density away from the carbon, so this carbon will be taking electron density from this system over here. So you're losing electron density in the orbitals in that region. What that does is it lowers the overall energy of that orbital. So now what you see is that before, when we didn't have the what are called conjugating groups on there, the donating group and the withdrawing group, what you see is that the energy difference between the orbitals was large. Let me make sure this is... So we're looking at this one and this one over here. The HOMO of the diene with the LUMO of the dienophile. So the energy difference between these two orbitals was large, which means they're mismatched and they weren't a good bonding pair. But as you put donating groups onto the diene, and as you put withdrawing groups onto the dienophile, the orbitals become closer in energy, and you have a more favorable bonding interaction that can actually take place. So in conclusion, exactly what I just said. The donating groups in the diene and the withdrawing groups in the dienophile make the orbitals closer in energy. Okay, so now another big question, what you're probably wondering about this entire time, if you're confused, is what is the mechanism of the Diels Alder reaction? So Again, we have a diene and a dienophile, and we have the formation of the final product, which usually has this six-membered ring with the double bond at the back of the diene, which is actually going to be over here. You're probably wondering, how does this happen? Why do we keep representing it like this, where we have the arrows going around in a ring shape? Okay, well, the reason I didn't want to get too far into that is because that's actually a misrepresentation of what the actual mechanism looks like. It makes you think that you have electrons going around in a circle, which isn't actually happening. That's not how the Diels Alder actually works. It works more like a sandwich. So if you have that diene HOMO with the correct symmetry that we were talking about before, and you have the dienophile LUMO, what actually happens is you have the top half of the sandwich, which is the diene, and the bottom half of the sandwich, which is the dienophile, and it's like two planes that combine vertically. So this is like a ship, I guess, and this is like a plane that's landing on top of the ship. Or this is the bottom bun, and this is the top bun. And the orbitals that you have here that are going to be combining along this, I guess, axis here, there are the peanut butter that holds the sandwich together. So this comes from Clayden and Greeves. If you want a further explanation, I recommend you pick up that textbook. It's pretty good. You could probably find it online. So, as I said before, it is the vertical collision of the diene and dienophile. You can imagine them as two planes sort of, I guess, coming on top of each other in vertical space. How we choose to represent it is with that, I guess, concerted attack. So the cyclic movement of the pi electrons around in a circle. But know that this sort of implies that everything's happening in the same plane. What you need to understand is that it's actually two planes that are vertically landing on top of each other, with the HOMO of the diene interacting with the LUMO of the dienophile. Okay. So, another thing that you'll often hear about with the Diels Alder is something about the endo product, the so-called endo product. Okay, so if you have a Diels Alder product, again, how do you recognize a Diels Alder product? Typically you have a six-membered ring with a double bond. This is sort of the backbone of the diene. This is the backbone of the dienophile that formed the Diels Alder product. What you'll often see is that on the backbone of the dienophile, an electron withdrawing group will be coming off, and on this side, over with the diene skeleton, you'll see electron donating groups coming off. The endo product refers to the product where everything is on the same side. So the electron donating groups are on the same side as the electron withdrawing groups. The exo product says that the electron donating groups are on the opposite side of the molecule as the electron withdrawing groups. Typically there's two rules associated with this whole endo thing. The first one is that if you have a bridgehead, so that's this sort of thing that's going on here, then when you form the product, the endo product is preferred. The second rule states, and this is the one you'll see more often that we have to use in this class, is that the electron withdrawing groups are preferred on the same side as the diene substituents. So if you have the reactions that look like this, and you do the Diels Alder reaction on them, and you get your product like this, what you'll see is that the diene substituents, these groups over here, if they're on a dash, the electron withdrawing groups will also be on a dash. So it's the same thing as this. The electron donating groups and the electron withdrawing groups will appear on the same side of the molecule. These remaining two methyl groups will instead be pushed upward on the other side of the molecule. Okay, so why is this happening? The most reasonable explanation that I've seen is that if you have a diene and a dienophile, when you do the peanut butter sandwich thing, when the top bun lands on the bottom bun, what you have is nearby, I guess, electron withdrawing groups. They have these orbitals that are able to align with the diene. So the reason that they end up on the same side is because you have this so-called secondary orbital interaction where these guys are helping the reaction proceed. You could also see it over here if you actually have, this is kind of peculiar, you have a diene and your dienophile is actually just a second diene, but you see that the second set of p orbitals over here are sort of also in the same symmetry as these. So it actually stabilizes the transition state of the Diels Alder reaction. This is what I tried to look at in a 2D sort of model. It's the same system as the one over here. It's hard to see, but here is the back of the molecule, so that double bond right over here, and here is the orbital of the carbonyl. And you can see that they're going to meet in space and stabilize each other. Okay, and the last question is, why is the Diels Alder regioselective? This one is perhaps the easiest one to answer. So say we have an electron donating group on the diene and a withdrawing group on the dienophile. How will the Diels Alder product look? Well, if we have a resonance structure, we could show the donation of this group into here, and you see that the minus charge will end up over here in this resonance structure. Similarly, with the electron withdrawing group, if you draw the resonance structure here where it is withdrawing electrons, you'll see that the positive charge ends up on this side of the molecule. So if you look at these two resonance structures together, you'll see that the minus charge will be here and the positive charge will be here. So when you form the final Diels Alder product, what you need to remember is that you need to line up these charges. So over here, the minus and the plus are going to be adjacent to each other. They're going to be located here, and over here they aren't. So this is not the product that's formed. This is upside down. So the minus and the positive need to meet when you're finding the final Diels Alder product. Okay, so it's probably like many parts of this lecture that you didn't really understand. What I suggest is that you try practice problems involving Diels Alder, and then once you've done enough of those, come back to this lecture and some things will make more sense. All right?